Thank you for joining us today for our Hangout, a preliminary study using graphene to improve electrical contacts. Our host, Rod Martens, Principal Engineer at TE, is going to walk you through the properties of graphene and answer the questions, can we use graphene to improve the corrosion resistance and durability in electrical contacts? Rod, thanks so much for joining us. I'm going to go ahead and turn it over to you to get started.
All right, thanks, Rachel. I appreciate the opportunity to present this work that we've done in conjunction with Columbia University and Auburn University that discusses the use of single-layer CVD-grown graphene to enhance the properties of electrical contacts. So with that, we'll pull up the presentation. And here we go. Okay, just a few preliminary comments on the preliminary study. This is some very fundamental work we're working on. It's not going into a product, but it's interesting, and we thought we'd share it with the technical community. And I want to acknowledge my co-authors. This would be Professors Terrell, Kaiser, and Hone at Columbia University, and Professor Jackson at Auburn University. A little bit of background here. TE Connectivity, one of our core products, obviously, is electrical connectors. And my work focuses on the electrical contact interface. So this would be basically where the rubber meets the road, where we conduct the electricity at the interface. One thing I guess I want to mention is that if you look at a connector and you look at your phone charger, you'll see a little glint of gold in there. Now, why would we use gold? I think gold's a fantastic material for what we want to do because it's corrosion resistant, it's thermally conductive, it's electrically conductive. You add about 0.5% of cobalt or nickel to it, and it's actually quite durable and low friction. So we don't use it because it's pretty. We use it because it really helps enhance the properties of an electrical contact. Of course, the problem here is that gold's expensive, and as engineers, we're trying to optimize cost at all, in any way that we can. So we're trying to get layers of gold to perform at the same level. So as we get thinner and thinner in gold, two of the things we get concerned about would be thin layers of gold don't completely cover a surface. They're somewhat porous, and they can allow the substrate to be exposed to a corrosive environment. You get some insulating films on the surface, and then you're having to replug your connector to make it work. Additionally, the thinner that you go with the layers of gold, they're less durable, and that would make sense. You have less gold to wear through. Once again, then you expose the substrate, and you get some corrosion. So as we go thinner and thinner in gold to save cost, we're looking at ways that we can basically help the gold do its job, whether we're adding lubricants on top of it, corrosion inhibitors, doing things underneath the gold, etc. And this is where the graphene comes in. Can we use graphene in some way to use less gold so that it does its job? Talk a little bit about graphene just fundamentally. I guess I would argue graphene, carbon nanotubes, buckyballs, they're all still a bit on the upward swing of the hype curve, but if you've done any reading about the material whatsoever, I think you consistently hear that it's the strongest material that's ever measured. The modulus is up in the order of a terapascal, strengths of 130 gigapascals. I've shown a couple of images here in the upper right, some work done by Lee and others where they etched holes in silicon, transferred some graphene sheets over it, and then used a nanoindenter to essentially probe the suspended graphene to get some material properties out of it. So you can see they're deflecting in the orders of nanometers and applying loads in the order of nanonewtons to get these properties. So they're fantastic mechanically at those levels. It's electrically conductive. Lots of people are looking at it for, can we make transistors and other things out of it? Certainly beyond the scope of this talk. And then it's chemically inert and gas impermeable. And from my perspective, that's what really kind of struck a chord with me, are these some properties that we could actually integrate into our products and make them better? So just a little example on the right there with a penny that was half coated in graphene and exposed to a corrosive environment. You can see that the upper half of the graphene is still shiny, and then the bottom half it looks like a corroded oxidized copper penny. So we wanted to actually see if we could grow this stuff on materials that we care about. So we did some sample fabrication at Columbia, and I'll walk through the graphene growth process just a little bit. Typically, the recipe uses pure copper, and then the graphene is CVD, or chemical vapor deposition, deposited at high temperatures. So you can see we're annealing the copper at 800 C for 10 hours, and then we introduce hydrogen at over 1,000 degrees, and then the carbon source is methane for 30 minutes at 1,000. What's interesting to me about graphene is, you can use almost anything for carbons as a carbon source. In fact, I was just reading a paper the other day where they use Girl Scout cookies as the carbon source. So I don't know what MIT used, which particular brand, but anyway. In the lower inset, you can see this is a strip of copper that we grew the graphene on. And I guess a logical question is, how do we know if we have graphene on the surface? And Raman spectroscopy is the typical method used there, where we examine certain peaks in the spectrum here. And we focus in on what's called the 2D peak. And so that on the lower right there, we've blown in on that. So if you have a relatively sharp peak around 2700, that would indicate monolayer graphene. Now, as we get multi-layer graphene, what happens is that peak spreads out a little bit and it shifts to the right, to the point of you get a very broad peak much further to the right if you have graphite, which, graphite essentially is just multi-layers of graphene. We took that strip, and this was just kind of our basically look-see to see if it's going to work. And then we etched it with oxygen plasma to remove the graphene on one piece, left the graphene in place on another, and then did a nitric acid dip, which is basically going to really go after the copper. And you can see on the left with no graphene, we had significant corrosive attack of the copper. Whereas on the graphene, if anything, we may have decorated the grains a little bit, but it's very clear and very clean. So clearly the graphene is demonstrating some resistance to corrosive attack. All right, so it looks nice, but what I really care about is the electrical contact resistance. So if we have corrosion films on the surface, they're insulating, and we don't have good low-level, reliable electrical contact. So using an instrument in my lab, we're actually probing these surfaces and measuring the contact resistance right at the interface. We use a reference probe. So this was a 6mm diameter brass ball, plated with 1.5 microns of nickel and 5 microns of soft gold. So that's a nice, clean, soft surface that we use as a reference probe. And then what we measured was the bare copper control, where we actually grew the graphene and then removed it with oxygen plasma, and the sample that still had the graphene in place, and then a control sample that has copper with a nickel underlayer and a 0.75 micron of gold on it. So that would be a representative contact finish. Slide, we can kind of see what happened here. So the blue curve, which is a little bit higher in terms of contact resistance, is the uncoated copper. The red would be the graphene coated copper, which is behaving somewhat similarly to our gold coated control coupon. So this is very interesting. I guess I should note that the horizontal axis is increasing load. So we start at 1 gram and then we load all the way out to 100 grams. And then monitor the resistance, as it decreases. Once we're at full load, the same curves, we introduced a little bit of wipe or translation at the contact interface. Now this would simulate when you plug or unplug a connector. You're displacing some oxides, corrosion, whatever may be on the contact. And you can see in all cases, a little bit of wipe helped quite a bit. In fact, the blue one, we were able to displace that oxide and get it down similar to the controls that are shown here with the red and the blue. I'm sorry, the red and the green. Well, interesting exercise, but I was a little bit concerned with our controls in that we grew the graphene and then we used oxygen plasma to remove it. So the question is, well, when we remove the graphene off the control, did we actually then subsequently oxidize it by the oxygen plasma? So to create, I would call them pure controls, I want to be able to make sure that I have a known amount of copper oxide on the surface, which isn't necessarily as trivial as it might sound. To understand how the oxide grows, we want to make sure that we're growing the right type of oxide. So this would be cuprous oxide that would happen at temperatures below 200 C or somewhat, relative to room temperature. And then we want to age it so that we generate that specific type of species. And from this curve here, we can see that the relationship between time and temperature and the film thickness. The point here was I want to be able to grow a known amount of oxide on a copper coupon. So I'll first of all, I'll clean it, and then I'm going to oxidize it to grow a film on there that's measurable. If it's too thick, then it's an open circuit. We can't measure it. We don't get any signal out of it. So I'll walk through this little exercise right here, which is more fundamental contact physics in terms of anytime we bring two surfaces together, it's a function of the constriction resistance, which is dominated by the geometry and the resistivity of the material, and the film resistance. So do we have an insulating film on top of it? So for a clean contact, we would neglect the second term. The constriction resistance is essentially the resistivity of the base material divided by the diameter of the area in contact. So we know the resistivity of copper, and we'll estimate the contact diameter by just calculating the Hertzian diameter. So that's fairly straightforward. And that would be indicated by the black line over here on the curve. Now, once we start adding a film in there, once again, we have to consider the resistivity of the film, the thickness of the film, as well as the area in contact, and that would be either rho times d over A. So we'll add that in series with the constriction resistance, and I plotted in a few different film thicknesses corresponding to a few different growths, and chose one that would give us an order of magnitude or two above the clean condition, but still well within our measurable range. So continuing that exercise, just to verify a few things, if we start down here at the bottom, our calculated curves are down here for perfectly clean copper interfaces coming together. So the blue would be my calculation. The black dashed line down here is a reference from literature. You can see they agree pretty well. However, anytime you bring a surface, even if it's clean, you bring it out into the environment, you're going to have a few monolayers of oxygen on it. And that essentially will also bump the curve up a little bit higher. So then the upper black dashed line is once again from the literature for monolayers of oxygen on virgin copper. I took a copper coupon and then we electrocleaned it. So basically we etched all the oxide off and got down to bare copper, but then it's exposed in the laboratory environment. You can see we got very good agreement experimentally with the dashed line there. So, okay, good. We have a good foundation to work from. Then I took one of those electrocleaned samples and then aged it at 100 C for 2 hours to try to get up to what our calculated red dashed line was. We didn't quite hit it. It's a little bit off because the calculation assumes a perfect coverage of the film, no fracture, etc. So it didn't quite reach the 2 orders of magnitude, but it's definitely a bump in the signal, so we have something that we can measure. Now for the proof of the pudding here. Now that we know how to have a good control, we took some copper-coated coupons that were grown at Graphene Frontiers. This would be a incubator company that came out of the University of Pennsylvania in the Philadelphia area. Who I appreciate them growing some samples for us. So if we walk through the exercise once again, the blue curves are the copper. So the copper, before we electrocleaned it, this would be copper that has just been in the lab for a couple of years and has a normal oxide on it, was open circuit. We electroclean it, we make it clean, we bring it down to the lower blue curve here. And then we heat age it, and it comes back up to the dashed blue line. So we know that, okay, that's where oxidized copper is going to be. Now, if we look at our graphene-coated samples, the solid line is the graphene as received. And once again, it's certainly lower than the open circuit copper. but it's a few milliohms higher than the clean copper. But then we thermally age it at 2 hours at 100 C, and you can see that the results are fairly similar. They're a little bit off here because I'm plotting the median of 9 tests. So basically, we're not seeing a big impact of thermal aging here. It's again a preliminary study, but this is an initial data set. What's also interesting to note here is you can see these lines all drop down at 200 grams to a fairly low value. This is where we introduced a little bit of wipe to all of these interfaces. What's interesting is once you add the wipe, which breaks through oxides, etc., they all come down to about the same value. Just a couple of interim conclusions then. We've kind of demonstrated that single-layer CVD graphene grown on copper can have some impact to copper oxidation and give us lower contact resistance values. But then really the open questions are, you know, I know this is the strongest material ever measured, but if you recall earlier, they were testing in terms of nanonewtons, and our products use loads certainly in the order of newtons. So we're many orders of magnitude off there. And then also, well, what are the fundamental corrosion initiation mechanisms in CVD graphene? Because at a certain point, I believe that we can actually corrode through it. So let's look a little deeper there. Well, durability testing of monolayer graphene, this work was done by Professor Terrell's group at Columbia, where they took a blunt Berkovich tip. So this would be in a nanoindenter, where typically this radius would be in the order of nanometers, but for this exercise, it was blunted so that we can use it as a tribology tool. We're operating in loads of 10 micronewtons, and then the CVD graphene was grown on copper, but then it was transferred onto silicon oxide in the little square area shown in the center there. Using the nanoindenter, we were able to do some wear testing of the graphene, and we went back to using Raman, so we would have a 20 micron wear track and then do Raman scans perpendicular to the wear track at different areas. And now we're going to look at a different portion of the peak, basically. So you see off to the right is the 2D peak, where we know that we have monolayer graphene. But then by examining the ratio of the D to the G peaks, we can determine how defective the graphene is. So the thought is, as we're wearing on it, we're going to start tearing it or introducing defects into the graphene film, so we can use that as a metric for its durability. Well, in this slide, we're showing the 10 micronewton load at 10, 50, and 100 cycles. See that we're introducing more and more defects. So red would indicate that we've got a lot of defects in the film. Also, what's interesting is the frictional force is going up as a function of cycles. And this could be a couple of things going on here. It could be that we're bunching the graphene up ahead of the tip, kind of like bunching a rug up. And additionally, it could be that we're wearing a trough into the silicon as well, so we're getting a little bit more contact area, which would be higher force. Next exercise looked at the sliding velocity dependence on the durability of the graphene. And what was interesting here is that there is a very strong relationship with velocity, but the wear is worse at the lower velocities. And one hypothesis here is that at the slower velocity, there's longer residence time, so we can develop more adhesion between the tip and the graphene. But that work is ongoing, trying to figure out what's exactly going on there. And this would be more into the area of where Professor Jackson is looking at doing some modeling. So we'll move away from kind of the mechanical interrogation of the film to the corrosion. So to be honest, my concern with a lot of hype about graphene, carbon nanotubes, etc., is we project these wonderful from the nanoscale out to the macro scale. And typically you can't achieve that, and the main reason for that is defectivity. These beautiful hexagonal matrices of carbon atoms are grown on a large scale film, but however you examine them closer, these domains where the hexagonal lattice is intact is usually on the order of tens of microns increasing up to a millimeter, but you could consider it as a grain. Essentially, at the edge of that, rather than having 6 carbon atoms, you might have 7. And so it's a break in the structure, and then it reorganizes into a nice grain structure neighboring to that. But what you end up having is grain boundaries. And what we did here is we took a copper coupon that had a monolayer of graphene on it, and then exposed it to a chlorine vapor for 1, 3, and 5 minutes. And what you can start to see is a decoration of these grain boundaries. So this would be imperfections in the graphene. So we know then that it's not perfectly impermeable, because you can have corrosion that initiates those boundaries and then comes up and creeps over, the so-called good graphene, and then you end up back where you started. We have a film covering the entire surface. Now, is a case of, well, that's interesting. Can we make lemonade out of the lemons here? So previously that was a corrosion response. What I'm showing here is a plating response. So we took a silver strike bath to see if we could initiate plating through the graphene, and similar to the corrosion, we can initiate plating at the grain boundaries. So now what's interesting here is, I'm not convinced that graphene is durable enough to be on the top surface of an electrical contact. There's no way that it's going to be able to withstand the loads that we care about. However, can we exploit it by burying it and then plating on top of it? So now we have this basically an integral diffusion barrier built into the contact interface. So that's really where what we're looking at right now. So just a few quick conclusions here. At a high level, we were able to show that that it is somewhat gas impermeable. We could limit oxidation and generate low contact resistance with the graphene. We found some indications with slower sliding speeds causing higher failures. And then also we've shown where the corrosion and plating can initiate in the grain boundaries. Well, I want to end here with some ongoing and future work. So our main focus going forward is going to be seeing if we can actually embed this impermeable graphene membrane in some of our plating structures, and then do some modeling to that effect. Once again, that's where Professor Jackson comes in. So we're going to be continuing this work. Actually, we did receive an NSF grant for $400,000 split between Columbia and Auburn to continue this work. So I look forward to sharing more work and more results as it comes out as a function of this collaboration. So with that, I guess I will turn it back to Rachel for any questions.
Thanks, Rod. Yes, so this is the floor is open for any questions, and I can go ahead and maybe get started with one that came in. The question really is around some of the barriers you see in using graphene to improve electrical contacts. Can you talk a little bit about that?
Sure. As I mentioned, this is really, really early work. We don't have any plans to put this in a product. The biggest barriers for productizing this from our perspective it comes down to time and temperature. When we electroplate contacts in a normal environment, the strip is going through the plating line in the order of tens of meters per minute. And if you look back at the growth property, or sorry, the growth recipe, we're operating, on the order of 10 hours. So first of all, there's a wild discrepancy on the time. Second is temperature. We don't use pure copper as an electrical contact member that often. I mean, it is done. But remember, an electrical contact needs to apply a force to make contact. So we use the copper alloy to carry electricity as well as act as a spring. So if we subject some of the alloys that we use in connectors, such as phosphor bronze would be an example, brass would be an example, they would either melt under the processing temperatures, or they would be wholly unsuitable to act as a spring member, in the product. So those are the two biggest barriers right now. I know there's a tremendous amount of work on lower temperature growth recipes. We're obviously keeping track of that. You can grow this on nickel. We could do things like cladding approaches. We could even look at transfer approaches. But I would say time and temperature are the biggest barriers right now.
Thanks, Rod. So it doesn't seem like we got any more questions. However, we're definitely going to post the recorded version of this and provide you with an option to send in any questions that you might have. So with that said, Rod, we thank you so much for taking time to share this study with us. And as I mentioned, look out for the webcast replay. Thank you all.
Thanks, Rod.
Thanks, Rod.